you know, in fact, I came to this because somebody asked me about what you know about particle annihilations, when you have two different particles that when get together annihilate each other. And so there is a region with one particle, another with the other, and an interface where they change. Another thing, for instance, another example is harmonic maps. You have a harmonic map whose image is just the lines, the axes, right? So suppose you are in Rn and you do a harmonic map, but you force the image, it has to be just the lines, right? Then in the base domains, the domain partitions into the points that go into each one of the lines, and again, there is some sort of interface among the points that are decided to go to one place or another. So mathematically, it's rather similar. Some examples of price formation, where sellers and buyers, and there is some gap in between what one wants to get and what one wants to pay. In some sense, problems like flame propagations are also of the same type. There is an ignition temperature, and when you are below the ignition temperature, you have some gas flowing, and when you are above, it flows at a higher temperature, right? And so there is this transition surface where this takes place. There are problems in phase transitions, which are more complex, where you have the two phases of some continuum, and then there is this change of phase interface, and there are problems which are also of the same type, but a little bit more complex, because, for instance, in many of these problems, there is also a surface energy, and so what you have is not only a diffusion on one side and a diffusion on the other, but also there is the surface energy that links then the curvature of the surface to the densities on both sides. So there is also those type of problems. I'm not going to talk about it like that. Basically, there are, when you treat that, I think the flame propagation problem is a good example of what are the approach to these problems. You have the flame propagation, you have the area where the temperature is bigger than ignition, and there you have a diffusion process, Laplacian or something like that. The area where it is smaller, and then you have to decide what happens in between. And so there is sort of what we would call the soft model, right, or where it is assumed that the flame has some width. And so mathematically, that means that there is some sort of a smooth passage from one phase to the other, okay? And then you can do the sort of high limit approximation, where you reduce the ignition at just the surface of ignition. And then that means that there is some sort of discontinuity on the derivatives of the surface, okay? And so when you study the problems, you start to looking at it to find existence of this problem. The easiest thing to do, or the best approach, is to consider the soft problem, where the temperature, the flame covers a strip, and therefore the equation is not so dramatic. It's like a heat equation equal to some right-hand side, which is bounded, which determines that you put in the ignition temperature. When you want to study the geometry of the limit, then you have to make the width smaller and smaller and smaller, right? And so the ignition concentrates just on the surface, and that becomes a free boundary problem. And so for existence and regularity is worse, but for the geometric description of what happens is better, because it's a neat transition, okay? So we will see a little bit of that phenomenon here. So basically what there is a lot of literature, so what I wanted to sort of concentrate is to discuss several different types of interactions. In other words, I'm going to talk a little bit at the basic problem where you have sort of the two regions, right? A region where there is the one type, and the region where there is the other type, and the separation surface, okay? And there we will have harmonic functions in both sides and a phase transition. So another interesting type that we have been studying is when the segregation makes a jump. In other words, where there is a gap between the two species, okay? This is, when we thought about doing this, I looked a bit at the literature, and there are some very interesting examples. For instance, there is one where, there is ants are very aggressive. And so when there is a dense population, when there is a not big population of the ants, then they are more or less separated in groups without too much organization. But when there is a high percentage, high density of ants, then they group their nets in hexagons. And so there they form hexagons which are all separated by a strip of constant width. And I'm going to talk about some math we did about that. I'm going to talk about, also describe a little bit when the media, the diffusion is given by fully nonlinear equations as optimal control problems, and then I will talk a little bit more mathematics on that, and also when one of the species moves infinitesimally, is a local, Laplacian type diffusion, and the other species instead can travel at a distance, can do jump processes. So how they interact, because I think it's an interesting difference between the models, okay? So let me start just giving a little background. So basically, as I said, this is what I mentioned before about the case of the flame propagation, right? There is, in principle, we will look at two species that are that diffuse in some sense, right? And their consistency is penalized. In other words, when they are together, then they have sort of to pay the density of population for both decreases. And this is like the smooth problem, right? And then if you increase the penalization, in other words, you make the penalization sort of go to infinity, then the species completely separates. And then what is interesting there is to see what is the stability, the geometry of the interface. Okay. So let me give you this super baby problem to see what it's about, right? And so the super baby problem is the following. It says you have let's say you have a species U and V, right? And they diffuse according to sort of the one-dimensional Laplacian, UXX. But when they are together, when their densities is, when they overlap, right? Then you have to pay a lot. In other words, the function becomes very convex, okay? And so for every epsilon, basically in this problem, this is very simple because the difference, the difference satisfies is a line, right? So the difference is a line, and so the solution U epsilon the solutions are always positive because you have data positive, and this right-hand side will become negative if you have negative, so it forces the solutions to be positive, and then as epsilon goes to 0, this approximates more and more these two lines. So in the limit, U infinity or U0, let's say, will be positive here and 0 here, and V will be positive here and 0 here. So this is basically, this is the simplest model, the first model I said I wanted to discuss. So let me, for those that are, probably there are not many in the audience, but just for for those that are not so much in analysis, let me tell you why, when I say diffusion, what do I mean by diffusion, okay? And so I'm going, in this lecture, I'm just going to use, apart from fully nonlinear equation, I'm going to use Laplacian and some fractional Laplacian, okay? And so let me tell you what the fractional Laplacian is. The fractional Laplacian is, so is this formula, okay? I'm interested in the Laplacian to the 1/2, which is when S is 1/2, so here is n plus 1. And so basically, why is this a diffusion? What do I mean by a diffusion process? It means that an integral like that basically represents a gain-loss operator. In other words, I'm in the position x, right? And there is a particle as a diffusion, as a distribution of particles u of y everywhere, right? And then there are the particles are jumping, so there are particles that jump into my position, and there are particles that leave my positions. And so if I want to know what is the balance of particles at my position, right, then I have to, this integral accounts for the particles which are in the position y and are jumping into x, and the density of jumps is given by this kernel. In other words, the positions which are far away, there are less particles jumping into my positions. And as they get closer, there are more particles, right? And these are the ones that are going away. And basically, the Laplacian is a limit configuration of that. In fact, you know, when you look at the Laplacian, it's uxx plus uyy plus ucc, you know, why is this particular, why is this a special function, right, special equation? But really, you can think of the Laplacian as the limit of the average. Again, yes, I'm in the position x, and I'm surrounded now in a little ball by the densities uy, right? And if I take this average and I divide by the, I have, well, here I have the volume of the ball plus 2. It has to be, it's n plus 2, the radius of the ball to the n plus 2, because it's second derivatives, right? So if you look at that limit here, it has to be 1 over epsilon to the n plus 2, then that limit converges to the Laplacian when epsilon goes to 0, okay? And I think this clarifies, at least I find it is clarifying, when you look at the heat equation, right? It says ut equal Laplacian of u. Why is the heat equation special? Because the heat equation is basically saying, I am standing at this position, I am being surrounded by these particles, okay? And if the average of what surrounds us is bigger than my density, right, then I'm going to grow, right? The ut says if the Laplacian is positive, that is, if there are particles coming in more than the ones that are going on, then the function grows. And if the quantity, the density at my point is bigger, the function decreases. In other words, I'm trying sort of to revert to my surrounding averages, okay? And that's why if you take the heat equation and put some initial data, which is oscillatory, that immediately kills the oscillations and tries to smooth everything, okay? And so this is, so this in some sense is what will justify how things happen later, okay? Another thing that I will be needing later, I will need to use is the following, is that the half Laplacian, right, this is what I said, the half Laplacian also can be represented in the following way. So I'm in the space x of dimension n, right? And then I can write the half Laplacian just in that space, right? Which is this formula. But another way to look at it is the following, is I'm in the space x, and I'm going to extend my function to one more variable y by solving the Dirichlet problem. In other words, by extending to the harmonic function in one more dimensions. And if you do that, and you take the normal derivative, you can use the Poisson kernel to compute the normal derivative, and you realize that the half Laplacian of u is exactly the same as the normal derivative of u in this extension, okay? And this is very useful because it, in some sense, reduces a non-local problem to a local one. In other words, it allows you to use many classical formulas of the Laplacian, right, applied to this extension. So this I'm going to read sooner or later. Okay. So basically now, the segregation problem that we are going to look will be the generalization of 1D, right? We have several different species, right? And they, in some sense, diffuses among them, and they are penalized for being together. And so basically, in general, will be problems of the form, some operator, diffusion operator on uj equal to 1 over epsilon, which is the penalization, times uj's times some function that might be local or non-local of the other components. Okay, so in the example I gave before, then fi of ui was simply ui. Okay, so so the ui's, right, the f are positive, so the uj's are all subsolutions of a diffusion equation, and therefore they are automatically bounded by the boundary data, right? In other words, you have a subsolution of an elliptic equation, general, the boundary data bounds the interior, so my functions are all going to be bounded, no problem. And since the right-hand side change signs when you try to put negative values, then the solutions will be all non-negative. So basically, the solutions of this equation in general will be all non-negative and bounded above. And as long as epsilon is not 0, right, then it is usually rather standard to find solutions of this equation. You know, these elliptic equations, a nice right-hand side. You can apply many different techniques. In the problems I discussed at the beginning, some solutions are, the operators are of divergence form, where the Laplacian equation, right, is an equation which is divergence and non-divergence, right? You can write it as divergence of gradient of u, or you can write it as aij dij of u. And sort of, especially for these problems, they are very different, the two approaches. Sort of the general philosophy I have is that to study sort of initial existence of regularity, energy methods are sort of the best ones, right? And so you can easily find the existence of solutions that maybe are Helder continuous and so on. When you look at higher regularity, then the non-divergence approach is really the one that really tells you what happens. In a divergence, if you have a divergence equations, divergence of aij of x, gradient u, and aij is Helder continuous, you cannot show me a single solution. While if you tell me aij dij of u equal to 0, then you can show some super solutions and sub-solutions. Complex functions are solutions, and so on. The techniques are different for different problems. 57, I should hurry up a little bit. So there has been a lot of work in the first model I discussed. So the main results that we obtained, we did some work with, we consider work with Van Wallin, and it's smoothness of solutions and smoothness and the geometry of interface. So let me tell you more or less how it works. So basically, I'm talking now about the same problem I did first with one variable. In other words, I have Laplacian of uj equal to 1 over epsilon. I think I wrote it before. Oops, I didn't write it before. Okay, sorry. I had to put things together. I was not planning to use any things, so I put together things. Basically, the equation that I, let me see if I have it here. Yeah, this basically the equation we studied was Laplacian of ui equal to the sum of ui uj over epsilon. So that's the sort of the simplest, it's non-divergence form, and it's not hard to find solutions. The question is then when you want to look at the geometry of the solutions. And so let me tell you what were the difficulties we found and that we have to solve. So you have several components now, right? And if you have only two components, then you are basically in the one-dimensional case. In other words, you take one minus the other, and then you just, the UI, UJ cancels, the UI, UKs are different. Let me just write something. So basically, the problem we studied there was Laplacian of uj is the simplest ones, equal to sum of uj, uk, k different than j, right, divided by epsilon. And so when epsilon goes to 0, that forces all of the populations to segregate, okay? Now, if you have only two of them coming together, there is no one else, right? Then we are in the case of the two-dimensional case, right? In other words, you take the difference and you have Laplacian of u1 minus u2, let's say, is equal to 0. So this is a harmonic function, right? Independently of epsilon, it's the same harmonic function. And you let epsilon go to 0, and then you have that both are the positive and negative part minus the negative part of the domain. So basically, what you have there is you have a harmonic function, and the phase transition is a level surface of a harmonic function, so is everything fine. So what there is to prove? Well, the problem is that when you have more than one, then it's very difficult to system coming back. Right, so basically, and several comes together, you have to decide what happens, right? And so maybe that several comes together and some of them are very skinny, or the several comes together and they have some positive density going into a point. So if they are very skinny, you don't want that. And so we have to prove that there is not such a thing, that if one of the components is very narrow at some scale, then you can start entering dyadically and you kill it after a finite number of steps. So that means that this configuration does not happen. And then if that configuration happens, then, so now we know that we have sort of several, if you have more than one component, you can have severals, but they keep some positive density. And so what you can prove is that basically you can separate them neatly, and so you have that transition between these functions. And so this and this now become harmonic transitions, so they are regular, and then where you have a triple or multiple point, and we use there sort of some algorithm monotonicity formulas for multiple valued functions that basically allow you to show that asymptotically the components are like homogeneous of the same homogeneity. So it's basically like a conical configuration, and everything is regular. So this was the regularity theory for this problem. So one that was more interesting that we started, I did with Stefania Patricia and Veronica Quitalo, was what happens if there is a gap, as is in the example of the ants, right? I mean, how do you model the existence of a gap? So, you know, it's, the existence of a gap appears if you have, for instance, a penalization like this, right? You have so basically you have the Laplacian of uj is 1 over epsilon uj times, and then this penalization term is non-local. For instance, you can put the integral on the ball of radius r centered at a point, okay? So if I do that and I let epsilon goes to 0, then this quantity has to go, you know, then uj and ui have to be, one of them has to be 0 when this quantity is going to infinity, okay? And that means that the sort of the free boundary for uj has to stay at distance at least r from the free boundary of uk, okay? So basically, so this is like the example of the ants, and in fact there are a lot of examples in the segregation literature about that. You know, it's just like mussels, a group like that in the beach, and owls have some way of screaming to keeping away the other species. So basically, let me tell you so this is a mathematical theory here that we basically show then that we have a little bit like the picture I showed before, that we end up having these smooth channels in n dimensions where the surfaces are C1 alpha and are exactly at distance 1 from each other all the time, right? And then there are some triple points where the surface, one species, where the interaction is changed from one species to another, okay? And we deduce a free boundary condition. Okay, we study the problem. We study the problem for p equal 1 and infinity. For p equal to intermediate, we just show existence and so on. But for the geometry of the interfaces, we pick 1 and infinity. And in the case of infinity, which is the one which we know more carefully, then you have an interface condition that says that the ratio between the normal vectors at opposing points, each point has a unique opposing point, and the ratio between the normal vectors is proportional to the Gauss curvature, the product of the curvatures of the interface in each side. In other words, if you have like a ring, if you have a configuration which is like the one species which is a circle, and then the other one which is a larger circle, parallel circle, right? Then the normal derivative, in other words, the species which is more whose habitat is concave, needs to put a higher normal derivative than the opposite one to sort of resist there. Okay, so now I want to discuss these two problems, the non-local, non-local, and this I want to discuss a little bit more in detail and give you some of the mathematics. Okay. So basically, the question we wanted to look at here, then it is like the first species, right? In other words, you have Laplacian, but the issue is if one of the species has, it has a jump process. It could be a flying insect, or could be plants that are carried by the wind. So you have these two, and then the first question you ask is, okay, well, what do you expect, right? What do you expect to happen? So we write again the basic penalization method, right? I'm going to discuss things pretty much with every S, but I'm just going to discuss the 1/2, which is easier to discuss. Okay. So basically, we have this, and again, if you take the difference, then you have this relation that is Laplacian of u epsilon minus Laplacian to ds of v epsilon has to be equal to 0. Okay. And so when you let epsilon go to 0, then you ask what happens. Okay. So basically, what happens when epsilon goes to 0 is that the two, again, as usual, the two species are going to be disjoint. So you have u in one side and v on the other. Okay. In the part where u is equal to 0, the Laplacian of u is equal to 0, right? There is nothing to say, okay? Now, but if you have a fractional operator, the operator in the set where the function is 0 is not 0 anymore. In other words, if you do, I don't know if I wrote it, yeah. Okay, so you expect again adjacent supports, right? But if you do, but now we said, okay, in the region where Laplacian of, in the region where Laplacian of where u is bigger than 0, right, we have, in the part where, yeah, where in the interior of place where u is equal to 0 and v is bigger than 0, Laplacian of u is equal to 0, because u is equal to 0 forces is infinitesimal, the Laplacian of u is equal to 0, right? And Laplacian of v is equal to 0 because Laplacian of v minus fractional Laplacian of u has to be equal to 0. So in that region, everything is as usual. But when you look at the region where U is positive, where V is 0, Laplacian S of V is not 0. And let me okay. Right. In other words, suppose that you are looking at a solution. So you have Laplacian to the 1/2, let's say, or to the S of V, right, equal to 0 in this region. Okay, so V is some positive function, right, is equal to 0 because here to 0. Then what is the Laplacian of the fractional Laplacian of V here? Well, you know, I have to do the integral of V of y minus V of x0, this is x0, over y minus x0 to the n plus 2s, right? But, you know, this integral is always positive. You know, here is 0, this is integral, and here is strictly positive. So, in fact, if you have a Laplacian of V equal to 0 and just in one dimension in this direction, then here V is like x to the s. That is the power of a Laplacian. And here V is, and the Laplacian here of V here, Laplacian to the s of V here is 0. But here V is 0 and the Laplacian to the s of V is equal to 1 over the distance here to the s. In other words, you cannot just now is not again the same game as before. So basically, we realize first that the Laplacian of U there is not 0 anymore. So the problem is not that easy as you thought. And then the other thing is that fractional Laplacians cannot carry mass in a surface. You know, the Laplacian can be a distribution on a surface, right? If you take the function absolute value of x, right, then the Laplacian is 0 on one side, 0 on the other, and it's a delta at the point, right? In other words, the first derivative of absolute value is the jump, and the second derivative is the delta. Okay, so in the previous problems that we looked, which were just infinitesimal, the interface always carried a measure. Okay, here the Laplacian to the s of V cannot carry a measure there, and therefore the formula that says Laplacian of U minus Laplacian to the s of V equal to 0 says that the Laplacian of U cannot carry a density there. Okay, so your solution has to be for U. What you have to solve is that Laplacian of U is equal to Laplacian of S of V when in the which is bigger than 0 on the region where U is bigger than 0 on the left in this picture, right? But also has to come tangentially all along the interface to 0. Okay, and so this is a much more delicate problem than the previous ones. So basically the way we did this is work I did with Patrizzi. What we did then is to use a subsolution approach. Okay, so what is a subsolution? A subsolution, you want to have basically you want to have a subsolution. So a subsolution will be you have prescribed U and V, the right data on the boundary, and what you want is Laplacian of U minus Laplacian of V, which is what in the limit is supposed to be 0, to be bigger or equal than 0. Okay, so what does that mean geometrically? Geometrically means that here you have, you have, let's say, what you expect. And so what you have is for the subsolutions, you have that, okay, V, you can make it a solution, and U is 0, and there you split U, you can split U in two parts. One is the harmonic parts that come from the boundary, and the other is the part that carries the right-hand side, okay? And then to have a subsolution, sort of the sum of both has to still remain positive. In other words, the part that carries the right-hand side has to stay below the harmonic function. Okay, and then what you expect is when you take the largest subsolution is that ut becomes tangent to u2 becomes tangent to u1 all along the boundary. Okay, and so let me give you some ideas how you prove it. So we started to have some, started with more or less simpler configuration, which is our domain is going to be a Lipschitz strip. Okay, so an infinite Lipschitz strip, and so here, oops, so okay, so here on the right we have v equal to 1 and u equal to 0. On the left, v equal to 0, u equal to 1, right? And then we have our subsolutions, and in the limit we expect a subsolution. Okay, so basically the first thing idea of good about this configuration is that if these things are Lipschitz graphs, then that forces the free boundary to be Lipschitz graphs. And the reason is the following. So suppose you have a subsolution and you move it a little bit if you move it a little bit down, right, if you take your subsolution and slide it all a little bit down, then here u was positive before, u became 1 before and was less than 1. Now u become 1 a little bit behind. And here v1 becomes 1 a little bit ahead. Okay? And so this is, if the previous was a subsolution, this is still a subsolution, because it still has the condition on the jump over here, but it's smaller than the other one. It's smaller than 1 here and bigger than 1 here. Okay? So if I slide this a little bit back, that is still a subsolution and should be below my largest subsolution, which is my solution. But since the function is Lipschitz, then I have room to move it a little bit right and left, right? In other words, I move it down, so it's just down at distance h from the boundary. If I move it a little bit right and left, it still stays below the boundary here and above the boundary here. Okay, so that's again a subsolution. In other words, when I take the soup of all subsolutions, then I can take any subsolution and then I can slide it down and move it, and that also qualifies as a subsolution. Okay, what is the implication of that? The implication of that is that the limiting solution, the interface, is Lipschitz. Okay, because if I have something which is too steep, like this way, when I move it a little bit, it's going to cross the limiting, the largest subsolution. Okay, so Lipschitz regularity, the Lipschitz properties of this forces the interface to be Lipschitz in the limit. Okay, now we want to prove that indeed the limit, that is the largest subsolution, all the normal derivative becomes 0. In other words, that for the largest subsolution, u manages to become tangentially to 0 at every point of the free boundary. That is, that up to now, it just was non-negative, so it became maybe with some normal derivative. And this is achieved so this is achieved by, well, we need several observations. The first one is that, again, because of the translation argument, u minus v, that is, if I have u and I stick to it the v, which is minus v, which is negative on the other side, that is monotone decreasing, right? Because of the argument of translating the subsolution. Okay, and it's monotone decreasing on a full family of directions, okay? So we want to show that in the limit, what happens in the limit and the regularity of the free boundary, then now at this point I want to cross to the extension configuration, right? In other words, I was saying I have Laplacian of v, Laplacian of u on one side, and Laplacian to the 1/2 of V on the other, okay? And I just talk about operators. But now I'm going to identify Laplacian to the 1/2 of V with its extensions in a half space, okay? So basically now what we have is we have, okay. Now I need a couple of technical things. Let me quote several theorems that I need to prove the regularity of a solution and the free boundary. The first one is the boundary Harnack inequality. If you have equations that satisfy functions u and v that satisfies the same equation, okay? Same equation vanishes in a half space. So in this half space, u and v are positive, satisfies the same equation, are non-negative and vanish simultaneously here. Then the quotient of those two functions is Helder continuous all the way to the boundary. No matter that, in principle, if you go inside, you know, this is equations which are only bounded measurable coefficients, so it would be pretty bad. But as you go to the boundary, the quotient becomes Helder continuous, okay? Now, here I put a hyperplane, but really, you know, the equations Aij's, which are only elliptic discontinuous, are invariant under bilinear transformations. In other words, if you make a bilinear transformations, the Aij becomes M transpose times Aij times M, where M is the matrix of the bilinear transformation. So it's another matrix which is again positive, so on. So the boundary Harnack is invariant under bilinear transformations, okay? Now, so that means that if I take any Lipschitz domains, then the function here, the two functions here, are again, that vanishes on this boundary, are again Helder continuous up to this boundary, okay? Because I reduce the problem to the line. And if I have a function, two functions which are harmonic, that satisfies that equation around a flat piece of surface, which is a Lipschitz domain, also the boundary Harnack holds, because I can transform this domain into this by a bilinear transformation. And then I can append the domain, I can rotate, you know, this flat thing, let's say, is in this direction, and then I can rotate it to the right and to the left. In other words, my domain was the complement of a surface, and I open it like that, and that opening is also a bilinear transformation, okay? So the boundary Harnack theorem holds for any artifact like that. Okay, so what is that good for us? So now let me describe the problem I was describing up to now. Let me describe it using the extension theorem. Okay, so using the extension theorem, what we have is, when I started, I had u and v that they both live along this line, which is an Rn. Okay, and I have extended, and here along this line, V satisfies Laplacian, fractional Laplacian of V equal to something, right? 0 here, positive here. So now I do the extension, the symmetric extension. So U still lives here because the equation of U is here and the Laplacian is here, I don't have to touch it. But now, if I do this extension, the fractional Laplacian of V, which is convolving with this kernel, becomes V nu, becomes, you know, it's not an integral thing anymore, it's a value at the point. Okay, so basically the equation now becomes V nu is equal to 0 here, and V nu, which is a fractional Laplacian of V, is equal to the Laplacian of U here. In other words, in some sense, you have this surface, you solve for V, right? And then when you solve for V, the V nu gives you what the Laplacian of U should be. And then you build Laplacian of U just with that data. You have boundary data and you build the Laplacian of U, okay? So now what is good about that? So basically, in this region, right, in this region, V is a harmonic function, non-negative, and therefore satisfies the Harnack inequality that says that the value in all of this horseshoe is bounded above and below by the value here. And now it says, okay, now I have V here. This is I enter into a distance. I go away from the boundary, from the free boundary, a distance proportional to this distance, and then here V is harmonic, right? And is of order, some order here, then it is of, V nu is of an order less, that is, if here V is like D, here is V like D, right? And I'm at distance D, I have a distance, so D from some distance from the free boundary, then here should be, I'm sorry, D to, yeah, this is the distance, but V is like, I write this V to the alpha for some alpha, okay, which I want to prescribe later. So V is like D to the alpha here, is like D to the alpha here, the derivative is like D to the alpha minus 1, okay? So, but then this is Laplacian of U. So Laplacian of U is like D to the alpha minus 1, right? Which means that the function basically is 2 times better. So the function is like D to the alpha minus 1 plus 2, right? So the function U is C1 alpha, okay? So we have C1 alpha regularity. Let me tell you what is this alpha. This alpha, in principle, can change from point to point, but is some number between, a strict number between 0 and 1, okay? And this is because our surface is Lipschitz, right? And we prove in some other work I did with Rosotong and Serra, we prove a sort of Fragment-Lindelof theorems for fractional operators. In other words, if you have a fractional operator defined in the complement of a cone up to infinity, right, is like an homogeneous function, R to the alpha f of theta, okay? And the homogeneity for the fractional operators is between something 0 and 1, okay? So the fact that the domain is Lipschitz allow us to decide that the function, that V has some Helder decay all over, and it tells us the fractional Laplacian of U, then it tells you that in principle U should be C1 plus D to the alpha plus D to the alpha plus 1, in other words, to separate like that. Of course, all of this is if we prove that indeed U nu is 0 along the boundary, because if not, the linearity will beat this quantity, right? It will be this plus something linear, okay? So to beat the nonlinearity, we use 2 important properties of harmonic functions in Lipschitz domains. Okay, this is finishing here. To do 2 important properties of harmonic functions in Lipschitz domains, right? The first one is that the normal derivative is in L2. This is this was proven by Dolber in the 70s in some sort of more complex way, but it's a relatively, you can really prove it very simply because you take U, so you have a Lipschitz domain, and you have a harmonic function here, and then you take U, and this direction is E, and you take U and UE, and you write the standard formula, Laplacian U, UE, minus UE, Laplacian U in the domain is equal to U nu UE minus, I'm sorry, this is Laplacian of UE, minus U UE nu. This is 0 because this is 0, this is 0 because everything is harmonic. There is some part of this which is far away, right? And so this is equal to the part which is far away over here, right? But since the domain is Lipschitz, the normal derivative always form an angle less than 90 degrees with UE. So U nu UE is like U nu square or UE square, comparable to both. Okay, and so basically to prove that U nu is 0, U nu is an L2 function, so you have to prove that it is 0 almost, which is 0 almost everywhere, Okay, and so you have to take a point on the boundary where you knew is a point of differentiability for you knew, and then if the function hits at an angle, you can make a small perturbation, move it a little bit forward, and find a better subsolution. Okay, so that is the way we prove that the solution is C1 alpha. So this is basically the theory for the local, non-local, and let me just go. I still have a bunch of pages, but let me just talk a little bit at the case where the segregation corresponds to fully nonlinear equations, to optimal equations and optimal control. So optimal control sort of it means that it's more adapted to financial mass than to a species, but basically it's a nonlinear diffusion problem, right? That is the diffusion process that minimizes diffusion among a family of operators, right? So basically, the typical limit control is the following, right? You say you you are allowed. Suppose I'm standing here, right, and I want to do a random walk and want to decide what is the probability I hit the door before the wall. Okay, then if I'm moving according to making a little circle around me, if I move at a point around on a little circle around me, right, that is the Laplacian, the solution. The expectation of going through the door is going to be the harmonic function, which is 0 on the walls, because if you are by the wall, you more probably hit the wall. It's going to be 1 at the door, because you are just by the door, most probably you are going to go out. And in between, right, the probability of hitting the wall at this point, if I'm going to move in a little circle, is equal to the average on the little circle, right? But this was the Laplacian from the beginning. The Laplacian is the, right? So this is Laplacian equal to 0, okay? So if I move in a little circle, right, then the expectation of leaving through the door will be the solution to that problem. Okay, now suppose that you allow me to choose my random walk, right, point by point, right? In other words, you allow me to choose an ellipsoid. In other words, okay, I'm going to jump into an ellipsoid, right, that has some bounded eccentricity, okay? And so I can point my ellipsoids to try to minimize or maximize my probability of going through the door, okay? So basically then, since I can choose one at each point, what I want to find is the operator, right, that is basically will be the infimum of aij of x, dij of u equal to x at this point, right, point by point, among the family of all admissible matrices aij, right? And so to control the eccentricity is to basically say that aij will be, that aij is going to be, I was going to jump a lot. Yeah, it's going to be between two multiples of the identity, that is two multiples of the Laplacian, okay? Now, the solution of that equation, which looks completely wild, right, is a solution of a fully nonlinear equation. And there is this beautiful theory done by Krylov, Safanov, and Evans that says that such a solution of such operator exists and is a C2 alpha function, right? And then you can get more higher regularity. So basically the problem that Veronica did the study was you have two species and each one of them minimizes his diffusion property, so you know, and so has satisfies the fully nonlinear equations, okay, and so they are managed to be disjoint, they don't segregate, okay? They segregate, okay? So let me tell you what that problem, in fact, that operator, I have about 5 minutes, more or less. Okay, so So that operator basically it has, you can really give a formula for u, although it's a little bit wild formula. You take u, you have to take all the eigenvalues, you multiply the positive eigenvalues of the square of u by little lambda, right? The negative by capital lambda, right? The positive by little lambda, the by capital lambda, and if you find a function that satisfies this equation at every point, that's the solution of f of the square of u. Okay, so it is, as I said, it's remarkable that such a solution exists and is so smooth. Okay, so basically, Veronica proved existence of Holder solutions, right? You have the two disjoint domain, and each one they satisfies this equation. She proved that the solutions are in fact Lipschitz continuous across the interface. Inside they are C2 alpha because they are solutions of the fully nonlinear equations. And they are smooth above outside. Okay, and with Veronica, Monica Torres, and Patrizzi, we look at the regularity of the interface and the regularity of the solution and the interface where you change from one to the other. And basically, so basically, we prove regularity, C1 alpha regularity in the interface, and that involves a bunch of steps, which I'm not going to enter to because it's like 10 pages. But basically, let me see if I can catch the first thing. Okay, we have the usual equation, right? F of one minus f of the other equal to 0, okay? Then you can prove that the solutions are Lipschitz. This is what Veronica proved, the solutions are Lipschitz. And then the next thing we want to prove, is that not only they are Lipschitz, but they have the same slope. So basically, if it's non-trivial, if we have a tangent plane, then will be the same for both, okay? And so the fact that it has a tangent plane from both sides comes from a monotonicity formula. So there is this monotonicity formula for subharmonic functions that I wrote with Friedman and Alt years ago that says that if you have two subharmonic functions in adjacent domains, then this quantity is monotone. And this quantity, so this quantity is, if you want to more or less have an idea of what that means, you have, you take a r square with this rho to the n minus 2, and it's based some sort like averaging the gradient square. And another r square with this one and averaging this. So these quantities, r squared times this and the other r squared times this, is like an average of gradient square of u. And so you can, so this function is monotone, means that if you go to the origin, it will have a limit. And if the limit is different from 0, that means that the two functions that we are coming together in this that this finite domain was basically a plane asymptotically, and these two functions were linear. And we know from the Veronica words that then these two linear functions have to coincide. And once you have that, then to prove, so you prove that if the you prove two theorems. One is that the free boundary is flat, then it's Lipschitz, and then if it is Lipschitz, it's C1 alpha. And this is an adaptation of an old technique, which is in a series of papers called a Harnack inequality approach to the regularity of free boundaries. And I don't have time to discuss much of that. So thank you very much.
A couple of questions. Antonio?
Yeah.
In the mode that you have to your right-hand side, the non-local term on the right-hand side.
Yeah.
The kernel was local. And you have the one non-local somehow. I mean, if you put on the right-hand side a non-local kernel, would you expect to have something like, I mean, maybe for these strips, these Lipschitz strips or something like that, also the segregation, but maybe not the gap between them?
Yeah, I think so. Let me say what was the reason, because I thought about that. If you have a gap, I think then you can move the non-local term, could advance the non-local term a little bit. I think that was the reason. But I thought about that, yeah.
You have a degeneracy there that you may shift.
Pardon?
You may shift the solutions.
The fractional thing, because the fractional thing, I mean, the gap you mean would be because it's a degeneracy in the Laplacian, right? Right. So but then the species which is in the other side can move and advance. Yeah.
Okay, anybody else want to ask a question? As a matter of fact, I would be interested if there's some biological reason for this action over a distance for the non-local action. For example, for the ants, what is the non-local action, the non-local agent between the ants?
No, there is the ants are the ones which just satisfies the second order. But if you have bees that are fighting the ants, then the bees, right, can travel at jumps. Mm-hmm. If you are talking, there are these. One example I found in the literature is there are, these seeds that are like a small that the wind carries around every spring. Okay. Certainly in Texas, I probably in Argentina too, right? I don't know. We call it panaderos. Because it has a little seed in the middle, and then it has like, what is it? Is it Mexico name for that? You don't know. Okay. Now, at some moment, and the wind carries them around, right? And they go and see everywhere. And there are many species like that propagate, where the seeds propagate at a distance. Okay, so this will be a non-local, the non-local part, right? Okay. And so if that interacts with another seed that doesn't travel, this will be two different, yeah.
Okay. Thank you very much. Well, if there are no more questions, let's thank.
Okay.
Thank you very much for being with us here. Celebrate.